Okay, I want to tell you about Gauss's law and how it relates to non-uniform cylindrical charge distributions. Non-uniform cylindrical charge distributions. That's just trying to figure out what that means it takes a moment. So let's take a look at what that means. Here's a cylinder, and the charge in this cylinder is not uniformly embedded throughout it. It's rather distributed in kind of a weird way. It's distributed as described by this equation. This equation is saying that the volume charge density, how much charge there is per volume, is equal to beta times R. So as you go out, the charge density is getting greater and greater and greater. I tried to show that in the shading. Like, do you see how it's not it's pretty light right at the center. In fact, I want it to be 0 at the center. And as you go out, the shading gets greater and greater. It gets darker and darker. And I'm trying to show that so that there's more and more charge density as you go out. Okay, so that said, then, if I wanted to know the electric field, say right here, a distance r away, let me bring it out a little bit further. If I wanted to know the electric field, say right there, then what I'm going to do is I'm going to put in a Gaussian surface in there. Should I go down a little bit? That's my Gaussian surface. It's a cylinder, and I'm going to call this the radius of the Gaussian surface. I'm going to call it r sub g. Okay. And at first you might think, oh, this isn't so bad. All I'm going to do is I'm going to find the charge enclosed, the sum of all the charge enclosed by the Gaussian surface, all over epsilon naught. That should equal, that's one way to find the net flux through the surface. That's how you find the net flux through the surface, but you can also get it this way. So it doesn't look so bad, but here's the problem. How do I know how much charge is enclosed in that Gaussian surface? It's varying. As you go out, it's getting greater and greater charge density. And so what we have to do is we have to look at this in terms of shells, concentric or coaxial shells. So these, think of a very tiny shell and another shell and then another shell and then another cylindrical shell and another cylindrical shell and so on. If I found the charge in each one of those cylindrical shells, that would be, and then added them up, that would be the charge enclosed. Okay, so I'm trying to find the charge in each cylindrical shell. Let me draw you one of the cylindrical shells I'm talking about. It's looking like this. It's in here, and it's a shell that has a little bit of thickness. It needs to have a little volume. So what I'm going to do is I'm going to show you that's the inside. Here's the outside. That's a, I don't know if you see that, but that's a shell. It's a cylindrical shell. Let me draw that out here so we can take a look at it a little better. I'll make the thickness a little bigger so that you can see it. Okay, let's say that the height of that shell is h. Of course, this shell is in there, but the height of the shell will make h. The radius of the shell, we'll call that r. And the thickness of the shell, that the distance between the outer and the inner shell, that thickness is going to be dr. So this little thickness right here, that's dr. Now you might say, hey, does it go out to the inside of the shell or does it go to the outside of the shell? And I would say it doesn't matter. It doesn't matter because the thickness of the shell is dr thickness. That's infinitesimally thin. And so if the thickness is infinitesimally thin, then it doesn't matter if I go to the inside or the outside. That's pretty much R, or R plus dr is about the same quantity. Well, if these are really thin shells, you might guess that we're not just putting in like a lot of shells into this thing. We're putting in an infinite amount of shells in here. Well, the charge that's enclosed in one shell, the charge that's enclosed just in one shell is a very small amount. It's dq. But this is what it's equal to. dq, the amount of charge in a shell, I'll call that dq sub shell. That's equal to the rho there, whatever the rho is, and I know rho is beta r. So it's equal to the rho there times the little volume. So the little volume of the shell is if I cut it and roll it out. So I'm cutting that right there and I'm rolling it out. And so this is what I get. Let's see, what is this volume? This volume, dV, what is it? Well, it's got a height h. It has got a length of 2 pi r. And it's got a thickness of dr. So if you want to know what dV is, I'll tell you what dV is. dV is equal to the height times the width times the length times the width times the height. So it's going to be h times 2 pi r times dr. That's what the dV is. So the charge that's enclosed in there is going to be rho times that volume, which is h 2 pi r dr. Now, why is that the case? Well, because remember how rho is q over v? Well, if you want q, then you just multiply rho times v. But when you do that, you have to use the rho at that location, not just any old rho. You got to use the rho at that location, and the rho at that location is this. Okay. So the charge enclosed in this shell is this, and you might guess that this, to get the charge enclosed by the Gaussian surface, all of the charge enclosed by the Gaussian surface, I'm going to use an integral to sum that up. Okay, so this is what the integral is going to look like. So the charge enclosed is going to be, doing Gauss's law, it's going to be the charge enclosed, let's see, from 0 to the Gaussian radius of rho dV that's dV. That is the charge enclosed over epsilon naught is equal to E dot dA. Now E, at every location, E is parallel to dA, except for the top and the bottom, where the dA is straight up and the E is out that way. So the E, like right here, is this way, and so is the dA. So I can get rid of the dot product. I can argue that the E isn't any stronger here than here, than here, than here, than here. So I can pull the E out of the integral and sum up all the dAs. And all the dAs, if I cut this and rolled it out, all those dAs would give me h times 2 pi rg of the Gaussian surface. So it's going to be E times 2 pi r g times h. See you in the next video.